In this lesson, we're going to be learning how to sketch a graph of a polynomial using the key features of the equation. Some key things we need to know when we are sketching the graph. We will use the x-intercepts and the y-intercepts, the degree and the sign of the leading coefficient in order to draw our key points. Remember, our x-intercepts are also called our roots, or what makes the polynomial 0. So x p of x equals 0. And the y-intercept is the constant of the polynomial equation. When we have the x-intercepts of the graph, we call them the roots. They correspond, the x-intercept of the graph correspond to the roots of the polynomial equation. We knew that from yesterday's lesson. Determine the zeros of the polynomial functions from their factors and use factor theorem to express the polynomial in factored form. So key points here, these are the bits of information we are looking for to find our key points and some key features. And the way that we're going to do that is by factoring the equation fully. When we talk about the multiplicity of the zero, remember this also means the multiplicity of the root, or the multiplicity of the factor, or the multiplicity of the x-intercept. All of these words mean the same thing, right? If a polynomial has a factor, x minus a, that is repeated n times, then x equals a is a 0 of multiplicity n. Let's go away. There we go. Multiplicity n, meaning we can represent it in this way. The multiplicity of a 0 can also be referred to as the order. So that's another word for multiplicity. So the order of 0, or the order of the root. And the multiplicity or the order of the root helps tell us what the shape of it is going to be. So a polynomial that has an x-intercept with an odd multiplicity, the y values will change signs, and the graph crosses over the x-axis, so it's going to change signs. Meaning, if this is our graph, it's going to go from the positive y values to the negative y values, or from the negative to the positive. One way or the other, it's crossing the x-axis. If, however, the polynomial function does not change signs at the x-intercept, we call that an even multiplicity. Means it stays above the x-axis or below the x-axis. So it approaches it, touches it, but doesn't cross. So here's an example. These are all zeros with multiplicity of 1, meaning they are even. Sorry, meaning they are odd. So you can see that the y values of this graph go from the negative side to the positive, from the positive side to the negative, from the negative side to the positive. Every time we cross one of those pink dots, the signs of our y values change because our multiplicity is an odd number. So if I have a situation where the multiplicity is 2, then I have a 0 where the y values are positive before and after I have touched that 0. So this is what we call, you can think of it as a bounce. Remember when we did parabolas in pre-Cal 11, we called it the bounce x-intercept. It does not cross the boundary, it just hits it and comes back up. And another example here, multiplicity of 3. So here we have a cubic, I believe, crossing over the x-intercept. And again, or the x-axis, sorry, we have y values negative. We cross over the pink point, and now our y values are positive. So odd multiplicities give us a change in y values, so we're crossing over the other side. But even means we are touching it and going back to where we came from. When we look at transformations, transformations are going to be another useful tool for us to graph our polynomial functions. Remember, we did transformations in Unit 1. So we are going to use this idea in order to help graph some of the base functions. So again, here H and K represent the translation, so left, right, up, down. And we have A and B represent our stretches, so either compression or expansion. Oh, I'm terrible at this spelling business today. And then the signs of A and B, whether they're positive or negative, will also tell us the direction. And this chart kind of summarizes what we already know about transformations that we did in Unit 1. So I'm just going to scroll right over it here. So in example 1, for each of the given functions, or each of the graphs, sorry, determine the least possible degree. So what is the smallest degree that it could be? Remember when we talked about in our lesson 1 of polynomials, we talked about how a cubic function and a quintic, so degree 3 and degree 5, could look similar if there aren't any transformations applied to them. So the least of the two would be a degree 3. So the more transformations that we apply to a graph, the easier it is for us to see what degree it is. So if we're not sure, we always choose the least possible. We want to know what is the sign of the leading coefficient. We're going to use the x-intercepts and factors to determine as best we can information about this graph. And we're going to identify on what intervals is the function positive and on what intervals is it negative. So essentially we're going to say for what values x is y positive, for what values x is y negative. So looking at A, we have a graph that looks like this. And we know that it is extending in both directions. One side is going up and one side is going down. So I know that this is an odd function graph or an odd degree polynomial. I can also see that there are 2 x-intercepts and 1 y-intercept right there. So 2 x-intercepts, they are -4, 0, and +1, 0. The x-intercepts, what kind of multiplicity does it have? Which one has a multiplicity of 1? So an odd multiplicity means we cross over the barrier. And we can see that multiplicity of 1, it's the -4, has a multiplicity of 1. The intercept that is at +1 touches it and comes right back. So the y values are negative on both sides of that x-intercept. The least possible degree, this looks like a cubic to me. It cannot be linear because it's not a line, and it cannot be quadratic because it's not a parabola. It must be odd, so that leaves me with the least possible degree is 3. Now, the extension of the graph, it starts off in the top left corner in quadrant 2 and extends down into quadrant 4. This tells me that the coefficient is negative, right? And we did this again in lesson 1 of polynomials when we talked about the characteristic features of a polynomial function. The factors are, so I know my x-intercept is -4, so one of my factors is going to be x + 4, and the other factor is going to be x - 1. I know that the multiplicity of x + 4 is 1, and the multiplicity of x - 1 is 2, so this is going to be x - 1 squared. Okay, because the multiplicity tells me the direction of the graph at the x-intercept. Because I have a bounce, I know that it's an even multiplicity. And because I'm saying that it is a cubic, I need to have 3 x's. So I get 1 x from this bracket, and I'm going to get 2 x's from this bracket. Now, where is the function positive? For what values of x is the y values positive? And the only time it's positive is up here. So that means x from -4 to the left. So that means x has to be less than -4 in order for the y values to be positive. And for what is it negative? Well, it's got to be on the other side then. X will be greater than -4. We're going to do the same analysis for this picture here on B. Now, because I don't want to scroll too much, I'm just going to do some key features on here. And then we're going to copy the information down below. So x-intercepts here and here. Y-intercept somewhere here. I can see that it's going from 2 to 1 in the quadrants. My x-intercepts are at -4, 0 and +3, 0. In both cases, I'm going from positive to negative, crossing the boundary, from negative to positive, crossing the boundary. So I know these are going to have odd multiplicity. Looking at this shape, I know it's for sure not a line, it's not a quadratic, and it's not a cubic, right? Quadratic is a parabola shape. This is more of a wonky W shape, which tells me that the least degree must be degree 4. Least degree must be a 4. So if we have odd multiplicity for these functions, then what can we say about our x-intercepts? Do we have any other x-intercepts? No, we do not. So let me just flip my page on here. I'm going to scroll down to our chart and fill in the information. X-intercepts are at -4 and 3. The x-intercept with multiplicity of 1 is at -4. And the multiplicity of 3 is at 3. And I'm going to show you why I know that that's a 3. At the -4 x-intercept, we are cutting across and changing signs. At the +3 x-intercept, we are also changing signs, which tells me it's an odd function. However, can you notice the shape? This kind of S squiggle shape there. This tells me, excuse me, that I have a degree or multiplicity of 3. It kind of follows the shape of a cubic graph. So that little squiggle, that movement where it does cut across, but it kind of has a little dip in the graph. This tells me that it is an odd function because we're cutting across, but the squiggle tells me that it has to be more than 1. So what's the next multiplicity after 1 that is odd? Well, if it's not 1, it's got to be 3. Oops, that was on the wrong. I highlighted the wrong number here. I got to go down to B here. Multiplicity of 1 and multiplicity of 3. So this gives me where the graph cuts across, and this gives me where the graph does a little squiggle. The least possible degree must be a 4. The graph extends from the second quadrant to the first quadrant. The leading coefficient in this case must be positive because the W shape is opening up. The factors are x plus 4 and x minus 3. And think about the multiplicity. X plus 4 has a multiplicity of 1. X minus 3 has a multiplicity of 3. So this one gets a little cube next to it. And here's how I'm going to check that I did that right. the degree must be a 4. So I have 1x here and 3 x's here. For what values is the function positive? So looking here, we are actually positive in 2 different directions, right? We are positive on this side of the graph, and we are positive on this side of the graph. So what intervals are we positive? X must be less than -4, or x has to be greater than +3. So on the outsides of the x-intercepts. And for what values is it negative? Well, it's negative in between those points. So between -4 and 3. So that's a visual analysis of graphs. Now we are going to look at analyzing an equation in order to sketch a graph. So we're going to work backwards here. Given the function, so we're going to analyze these two here. Given the function negative x plus 1 cubed x minus 3. This is in factored form, right? This is a factored polynomial. In order to identify the degrees, we're going to count how many x's are represented here. I see an x here with multiplicity 3, so this is 3 x's, and an x here, so that's 1x, so that means our degree is a total of 4. The leading coefficient, well, I see a negative out front, so the leading coefficient is negative, which means what does the end behavior look like? What do the ends of the graph look like? Well, one end is going to be pointing down and to the left, and the other end is going to be pointing down and to the right. We're going to have an even graph, right? An even polynomial that's negative opens downwards. So we're going from second quadrant to the fourth quadrant. What are the zeros or the intercepts? So what are the roots of the function? Well, I can see right from the factored form, it's -1 and +3. -1 has a multiplicity of 3, so I'm expecting a squiggle at that point. And +3 has a multiplicity of 1. I'm expecting a cut through that point. What about the y-intercept? Remember, the y-intercept is the constant of our function. And right now it's in factored form, so we can't see what the constant is. But let us do some analysis here. If I were to expand this bracket, I would get x cubed plus something something x squared plus something something x plus something something. The last bit will be the last number cubed, which is 1. Then if I multiply it through with this bracket, I'm going to get x to the 4 and then something something, all the stuff in between, and the constant will be 1 cubed, which is 1 times 3. So the constant here is -3. But I also have a negative out front. That means I have to put a negative in front of everything here, so this becomes a positive. So my constant is going to be at +3. 0, +3. If you are not sure how I did that without doing all the steps, then go ahead and expand. X plus 1 cubed, and then multiply it by -1 for the coefficient, and then multiply it by x minus 3. And if you collect all your like terms, you're going to get -x to the 4th, plus or minus some stuff in the middle, and your last number will be a 3, your constant. For what intervals is the function positive? Okay. This is where we got to, again, have some kind of a mental image of what's going on. Here is my graph. Here is -1, and here is +3, and here is +3. I know this is an x-intercept, this is a y-intercept, this is a x-intercept. I know my graph is pointing down and it's doing something in the middle like this. Okay, now I didn't quite draw that effectively because at +3 we have a cut through point. There it is, that's fine. But at -1 we have, oh dear, multiplicity of 3. So I'm going to come down and it's going to like squiggle through that graph there. Either way, I know that it's pointing down and these are my two intercepts and that is my y-intercept. So this is where it's going to be negative and this is where it's going to be positive. So let's write what that looks like. Where is it positive? It is positive between my x-intercepts. And where is it negative? It's negative on the other side of the intercepts. So -1, oops, let me just give myself a little bit more space here. X must be less than -1, or X can be greater than +3. And that's where it's going to be negative. Okay, so we have some information here. We could also find a couple other points when it comes to graphing this. But here is our function. Let's say -1 is right here. +3 is here. And 1, 2, 3, +3 is here. I know my graph will squiggle through and we'll cut through here down this way, and it's going to do something in between 0 and 3. We can take our function here and we can substitute a number just to find an extra point. So if I took my function and said x equals 1, what would y be? So let me just grab my calculator here. Y equals -1 plus 1 cubed times 1 minus 3. Oh, I didn't even need my calculator here. This is going to be -1 times -2. Oops. I did need a calculator. Well, I don't need actually, but I need to fix this. -2. There we go. This gives me 8, and this gives, or sorry, -8 times -2. This is going to give me +16. All right, I don't think I have enough space here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so it's going to be somewhere way up here. That's all right. So it's going to go from my y-intercept up to the top there, and it's going to come down and cut across. So this is my sketch. Using the equation, using some facts that we know that we've learned over the last 3 days. Is it super accurate? No, but I don't need it to be super accurate because it says just sketch. So as long as I can use some key points and some key pieces of information, then this is good enough, good to go. Let us take a look at the second one here. So in our second example, we are given a polynomial. And this one is in, excuse me, this is not in factored form. So not factored. So what we need to do is, first of all, let's just look at it and figure out what are some common things we can pull out. And then we can do some analysis. So I know from just looking at it that the leading coefficient is going to be positive. And I know that the degree is a degree 5. So let's see, where's my chart? I think it's just below here. I know I have a degree 5. I know I have a positive coefficient or leading coefficient. So my end behavior will be from quadrant 2, pardon me, from quadrant 3 to quadrant 1. Oh, and I just realized I had written something incorrectly on our last chart. This is going from quadrant 3 to 4. this is quadrant 3, and this is quadrant 4. Apologies for that. Okay, so that is pretty much all I can say just by looking at it. So we're going to try and do some factoring here. First thing I notice, I'm just going to erase my highlights here, they all have x's in them. So right away I can pull out an x squared. So y equals x squared. I'm left with 2x cubed plus x squared minus 18x minus 9. I see 4 terms in here, so I'm going to try factor by grouping. This is going to be x squared, 2x squared, x plus 1. Pull out a negative 9 here, x plus 1. All right, x squared, x plus 1, 2x squared minus 9. That doesn't quite look right. Oh, I pulled out a 2 here. And I shouldn't have because there is no 2 in my second term. So this is x squared, 2x plus 1. And then if I pull out a 9, this should have a 2 here. Okay, that looks a little bit better. So this is x squared, 2x plus 1. That's much better. X squared minus 9. Now to factor here, notice that this is a difference of squares. This is x squared minus 3 squared. And when we have a difference of squares, difference means we have 2 perfect squares with a minus sign in the middle. We can always factor them as a plus b times a minus b. So in completely factored form, I have x squared, 2x plus 1, x minus 3, and x plus 3. Awesome. Okay. Couple things we should notice. There is no constant in this term or in this polynomial. So that means my y-intercept is at 0, 0. If I have a point at 0, 0, that means one of my intercepts is also at 0, x-intercepts is at 0, 0, because both of them are 0 there. So this tells me I have an x-intercept at 0. This tells me I have an x-intercept at -1/2. This one tells me I have one at 3, and this one tells me I have one at -3. Let's look at the multiplicity.